In this video, we're going to look at question 5. So it says a constant potential difference of 2 volts is applied across the ends of a metal strip with the following dimensions: length 0.3 meters, width 4 millimeters, and thickness 10 micrometers. The metal has a resistivity of 1.5 times 10 to the minus 7 omega meters at 0 degrees Celsius and a temperature coefficient of resistance of alpha. And then the strip loses heat to its surrounding at a rate proportional to the surface area and to the excess temperature above the surroundings, theta, which are at 0 degrees Celsius. Okay, and then the constant of proportionality is 22 watts. Okay, constant of proportionality. And then the question wants us to determine, first of all, the resistance of a strip at 0 degrees Celsius. So we can just use the dimensions and the resistivity. So the first part, we should start off with the resistivity is equal to the resistance equal to the resistivity multiplied by L over A. And that should be equal to 1.5 times 10 to the minus 7 times 10 to the minus 7 multiplied by the length, which is 0.3 meters, over the total area. The total area should be 4 millimeters multiplied by 10 micrometers. So that is 10 to the minus 6, yeah. Okay. And then we can just plug this into a calculator. So we have 1.5 10 to the minus 7 multiplied by, this is 0.3 over 4 to the minus 3 multiplied by 10 to the minus 6. Okay. And we have 1.125, this is ohms. So then this should be the answer to the first part of the question. Now let's see the second part. So it says the electrical power transferred when the strip is at 15 degrees Celsius. So I suppose it says the temperature coefficient resistance is alpha, so we can just directly use that and then calculate based on the resistance at 0 degrees Celsius. So what we should have is that the new resistance should be equal to the initial resistance at 0 degrees Celsius and then plus a coefficient, right? It says the coefficient of resistance, so that should be something like this. It's not plus, it should be something like the initial plus the initial multiplied by a certain factor multiplied by the temperature. And temperature, we denote it by theta, the excess temperature above the surrounding, which are at 0 degrees Celsius. So we are assuming that the surrounding is at 0 degrees Celsius. So you can just use theta. And then based on this, we should calculate it out. So we have 1.125 multiplied by 1 plus alpha, which is 3.3, 10 to the minus 3, multiplied by 15, right? 15. It says, yeah, okay, 15. So that should give us 1.18 ohms. Okay, and then it says electrical power transfer. So we can just use this in power is equal to, over here we're given only the voltage, so we can just use V squared over R. So we have that is that is 2 squared, right? It's 2 squared, yeah. So 4 over 1.18. So we have 3.39 watts, and that should be the answer to the second part. And then let's see the last part. So it says write down expressions for the power converter as a function of excess temperature theta, and for the rate of heat loss P as a function of excess temperature theta. Hence, estimate the temperature reached after a current has been passing for a long period of time. So I suppose, okay, so we need to express the power converted and the power loss in terms of the temperature, and then we can set them equal to each other. So basically that is when the thermal equilibrium is established, and that is basically the temperature reached. Suppose the terminal temperature reached. So first of all, the power converts as excess temperature theta. So this should be pretty simple. So we have P is equal to V squared over R, right? So we should have something like this. It's 4 over R, which is 1.125 multiplied by 1 plus 3.3 times 10 to the minus 3, right? Minus 3 times theta. And that should be the power converted. And then the other power is the power lost. And then it says over here, it says the strip loses heat to surrounding at a rate proportional surface area. So we can just say proportional to the surface area. So some constant K multiplied by A. Yeah, right. Some constant K, and I believe, yeah, so the constant K is 22. Yeah, it's given the question. So we can just do this. We have K times the area multiplied by the temperature. So we have 22. 22 multiplied by the area, which is how do we get the total area? Do we also consider the thickness as well? Or we can just consider the two sides. Well, if we consider two sides, there won't be a very large difference because the thickness is in micrometers. So even if we consider and we round it, it would not have any kind of effect, I believe. So we can just use the two sides. So we have 2 multiplied by the surface area, which is the length multiplied by the width, I believe. So 0.3. So that should be 0.3 multiplied by 4 millimeters. Okay, so, and then multiply by theta. And we set them equal to each other. Okay, I think it might be easier for us to convert them back into their variables to simplify the calculation. So we have R, which is R1 plus alpha theta. So we want to isolate theta. Well, in this case, suppose we multiply, yeah, we multiply both sides. And then we will get something like RKA theta plus, this is KA alpha theta squared. And then, wait, this is also R. It also has an R, right? Yeah, okay. And then this is equal to V squared. And we want to isolate theta. Okay, so basically this is just a quadratic equation. So we have RKA alpha plus this is RKA theta minus v squared is equal to 0. So theta should be equal to, first of all, it shouldn't be a minus number, so we can just assume that's plus. So it's minus RKA plus R squared K squared A squared. Minus, this is plus 4V squared RKA alpha over, this is 2 times RKA alpha. And yeah, I suppose we can just calculate this. We'll put this entire thing into an equation. So what we have over here is 1.125 multiplied by 22, no, yeah, 22 multiplied by, this is, okay, this is a rather, this is a rather gratuitous. So suppose we can calculate some variables first. So I suppose the most probable one is probably just the area. So the area is 4 times 1 is 3, multiplied by 0.3. So we should have 0.0012. Okay. And then this should be rather simpler to plug this in. So we have 1.125 multiplied by 0.00. 12 multiplied by 22 plus, this is the square root of r squared. R squared 1.125 squared multiplied by 22 squared multiplied by 0.0012 squared, and then plus, this is 4 times 4, 2 squared, times 1.125 times 22 times 0.0012 times 3.3, 10 to the minus 3. Okay, we're done with the top line now. Let's move on to the bottom. Okay, so on the bottom we have, we have 2, right? 2 times 0. Okay, and then multiply by 22, and then times 0.0012, and then times alpha, which is just 3.3 e to the power minus 3. And we have, why is this still loading? Wait, what? Okay, so then we have 101. 101. That seems a bit high. Okay, so well, suppose it should be the case. Yeah. Okay, and then so we have 101 degrees Celsius for the answer.